Hello, everyone. I'm Cosmo. I basically have put together some slides that are basically a summary for me to talk about the first 5 chapters of OSTEP, which is Operating Systems 3 Easy Steps, which is the book we are going through. The book is available online, and you can get PDFs of it for free, so I would highly recommend going and reading it when you get the opportunity, for those of you who have not yet. And yeah, so there's going to be roughly 3 parts to this. I have a lot of slides. Don't be too afraid. I'm not going to be spending very much time on any of them, although feel free to stop me at any point if you have a question or you want to talk about it. I'm not insistent on getting to the end of this. I want us to just all have a nice time, basically going over and talking about the content in, I'm going to call it OSTEP, because I think that's a nice way of talking about it. But yeah, going over the content in OSTEP. So yeah, there's going to be a bit which is basically an introduction to operating systems. There's a chapter on processes that I'm going to go over, and then there's a chapter on the process API. Chapters 1 and 3 are sort of more interstitial bits. So yes, hello, welcome to this book group. The book is called Operating Systems 3 Easy Pieces. It's named after a piece of writing Richard Feynman did, who's a famous physicist and famous for being very, very good at teaching, Richard Feynman. He had a book called 6 Easy Pieces about physics. Now, our book says operating systems is roughly half as hard as physics. And luckily, there are 3 pieces that the book is going to divide the field into. And those 3 areas are virtualization, concurrency, and persistence. At the end of some of the chapters, the book has homework, and it's pretty cool. I'd highly recommend engaging in it when you've read those chapters. And the book opens with this quote that's not from Confucius, but lots of people think it is. It's from another philosopher called Xunzi. That says, "I hear and I forget. I see and I remember. I do and I understand." So you should not just listen to me. You should read the book and then you'll remember. And then you should do the homework and then you'll understand. So yeah, we're covering chapters 1 to 5. This is basically the 3 chapters with meat in them are intro, processes, and process API. The introduction talks about the 3 sort of pillars of operating systems, and the segments following are going to focus on processes in particular as an instance of virtualization. These are the chapters in the book. So as you can see, most of what we're talking about today is going to fall into the virtualization section, but we're going to talk about all 3 sections in the introduction. So what's an operating system? Why do I want to have an operating system? Operating systems fundamentally are just a kind of program. But operating systems are programs that have been designed specifically for the purpose of making it easy to use other programs on your computer. So there are a couple things that aren't actually done automatically for you by a computer chip, like having multiple programs running at the same time. So like a CPU processor, it just executes instructions in order. Having multiple separate streams of instructions that are different programs all execute on the same chip is actually quite unnatural. You need a program to manage this for you. Also, interacting with the wide world of different types of hardware, like USB drives, network cards, disk drives, is actually quite complex, and each one kind of needs its own special treatment. It can be very annoying, if you had to, every time you wanted to write data into a file on your disk, had to write all the logic to talk the specific sort of hard disk drive you have in your computer. That would be really painful. So the operating system sort of contains code that does this for you. So basically, the operating system is a big program that makes writing your own programs and running them on the computer really easy. They used to be, they weren't always called operating systems. In the past, operating systems were also called executives or supervisors, or rather floridly, the master control program, which is, I think, an awesome name. The first of our sort of 3 pillars, and the primary mechanism used by the operating system to make it easy to run other programs, is called virtualization. It's a very, very general technique, and the shape it always takes is you have some physical resource on the computer. That could be like memory, or the CPU, or the disk, or the internet, that's talking to the computer. And it takes this resource and it transforms it into a more general, sort of powerful, easy-to-use virtual form. The book has these call-out segments called the crux of the problem. And the crux of the problem in virtualization that the book is going to talk about is how we virtualize resources. Because we just sort of accept that we want to do it. We want to be able to run multiple programs on the same computer. We want to be able to give multiple programs access to RAM or the internet. The difficult part is how it's done. And this is what the book focuses on. So to give you a flavor of why we want virtualization, where it comes in, we're going to look at this program. So the book has examples all throughout it of different programs written in C that sort of give you an idea of the particular topic. I have rewritten all the code listings in Rust because this is Rust and C++ Dragons. You have the C examples in the book. I'm also going to give you the Rust ones. So this program called cpu.rs basically just takes an argument on the command line called string, and then it loops, and every second it just prints the string out again. So if you built it and ran it, it would look like this. You run it with the argument A, and then it just prints A on every line until you stop it. Now, the interesting thing here is, if we imagine we're running on a computer that only has one core, the operating system lets us do a sort of interesting thing. You can run using this syntax in your sort of command line shell, where you run CPU A, CPU B, CPU C, CPU D, all on one line, each of them suffixed with this ampersand character. And because of the operating system, all of these programs are able to run at the same time. So you get as output, BCAD all in the same go, and then you get another BCAD every second. And this works even if your computer only has one core, which, if you didn't know anything about computers, you might think, this is super weird. How's this possibly happening? The processor should just execute one of my programs, and while it's doing that, it can't do anything else. So how is it that I'm getting all the output of these 4 programs all together? What's going on? And the answer is that the operating system is sort of hiding stuff from you. It produces an illusion of there being like an apparently infinite number of CPUs, each process getting its own special virtual CPU. And this is incredibly useful because it allows you to run 1,000 different things on your computer all at once, and it doesn't just completely lock up when you run the first one. But having to do this causes some new problems. In particular, you have to answer some questions. If you have 2 programs, both of which could be running at the same time, you can still only run one set of instructions on the processor at one time. So the operating system has to decide which of the 2 programs is going to be running. And the decision made is according to something called a policy. And the word policy is like a special word. It's a term that you should pay attention to and focus on when you're reading this book. It means something. And we're going to talk a little bit more about that later. Similarly, you can virtualize memory. So your computer will have some amount of RAM in it. You'll have put some sticks in it, probably fewer nowadays than you used to be able to afford. And this has this very simple conceptual interface where you have physical memory is basically just an array of bytes. You have bytes all in order, each of them with an address. And you have 2 operations you can take on memory. You have read and write. When you read, you just specify an address, and you get to know what's at that address. And when you write, you can specify an address and some data, like a byte. And then this byte will be taken and stored in memory at that address. Now, all programs need to talk to memory. In particularly, all programs are made of instructions. Instructions are stored in memory. So to even execute a program at all, you need to be constantly loading the instructions. So there is no program without memory access. And so here's another program I want you to consider. This program allocates an integer on the heap using box : new, and then it prints out a message saying, this is the address pointed to by this box that we've put on the heap. In particular, it prefixes this with the ID of the process, which is a unique identifier for the program that's running. And we use this raw pointer syntax to get out the address of the box. And this will make more sense once you see what the output of the program looks like. And then we do a very similar thing to our first program. Every single second, we increment this integer by 1, and then we print it out, again, with the ID of the process that's running. And the reason we're doing this is so we can disambiguate multiple processes we're running on the same command line. So now let's have a look at the output. You run it on its own, and it says, OK, I've allocated this integer at this memory address, 0x20000. And then every second, it prints out the value, increments it by 1. And you can see in these braces along the left, it's all process ID 2134. Now you use the same sigil we had before for running programs at the same time, and it says program 24113 put the integer at this address, and program 24114, different program, also put its integer at the same pointer address, which is like, okay, interesting, didn't know that could happen. And then you think, well, if they're both at the same address, then when they're incrementing these integers, surely they're going to work together. The first one's going to increment it, then the second one's going to increment it. So we're still going to see 1, 2, 3, 4. But no, both programs print out 1, then both programs print out 2. And wait, what's going on? Every single program has allocated its integer at the same memory address. But they somehow are updating these i's independently. It's as if each program has its own private copy of all the memory that is independent of all the other ones. And indeed, this is exactly what's happening. The operating system virtualizes memory. Every single running program gets something called a virtual address space, which the operating system maps onto the real physical memory that it controls. And the upshot of this, the really, really nice thing, is that when you have one program running, you can't affect the address space of another program. This is beneficial because you don't really want your programs to be able to trample all over each other. We move now on to our second theme, that of concurrency. And concurrency basically comes up whenever within a program you have multiple threads or sequences of instructions operating at the same time, doing multiple things at once. Particularly when it comes to operating systems, concurrency is like a problem to deal with more than it is like a benefit. The operating system was sort of the first place where people really had to deal with the problems of concurrency. And given the example you saw before of virtualizing the CPU, running multiple processes within the operating system at once, you can see why this would happen. The operating system has to juggle all of these things, processes and other things as well, all executing like semantically at the same time. And this leads to some problems. I'm going to show you another code example. But before that, I'm going to, this is the crux of the problem. When there are many concurrent threads going on in the same address space, how can this work? How can you build programs that work correctly? In particular, what does the operating system have to provide as an interface to do this? And what does the hardware have to provide? Like, do you have to do anything? Like, does your CPU vendor have to give special instructions for dealing with this sort of thing? The answer is yes. We'll see that later, but not in this particular set of chapters. So yes, the crux of the sort of concurrency problem is dealing with this and answering these questions. So we're going to give an example of a particular program that has to think about concurrency. This is adapted from the books threads.c. Now, this program is not a real program. It doesn't compile. And if it did compile, it would actually invoke undefined behavior. So don't look at this and think, this is a program that works. Look at this and think, here's the shape of some logic we might be trying to implement. So you have this sort of global variable, a static counter that's an integer and starts at 0. And our program prints that out, and then it defines a function. So this is like some of the slightly weirder Rust syntax. This is syntax for defining a closure. And we say that worker is the name of a function that loops some number of times equal to this variable loops that is passed by the user on the command line. And then each time around the loop, it basically says, let this variable val be equal to the current value of the counter, and then store to the counter the value of value plus 1. And this is a slightly weird way of writing it. Why haven't I just written plus equals 1? Basically, this is the way you should be thinking of it, as like being two separate operations. In particular, to make this compile, you have to use in Rust a sort of type called atomics. But this is sort of beside the point of the actual concern we have, which is that in this example, you then take this function and you run it on 2 different threads, which basically means you set up 2 different sequences of instructions that are executing concurrently. They're both doing the same thing. So T1 and T2 are basically names for these threads of execution. You create them both, so they both start executing, and then you call join on each of them. And what join does is basically waits until it's done. So after both of them have completed, you then print out the final value of the counter. So kind of question for the audience. If the program is run with the value of loops set to 1000, what do you expect the final value of counter to be? And while you're thinking about this question, I'm going to look back at the code. If loops, this variable in the number of times that worker loops for, if it's 1000, what do you expect counter to be at the end? Accepting guesses.
Fearful silence.
Yes. Kira, do you have a guess?
Oh,
Under
I,
2000.
th- I think it's 2000
You think it's
in
2000
this
exactly?
case,
Kira
but
says under 2000.
let's see.
So both of you are sort of on the right track. If there wasn't any funny business, then indeed it is 2000. And if you run this program on your computer, you'll very likely get 2000. When the two threads complete, counter is 2000. And sort of, if nothing weird's going on, you sort of think, well, like the loop increments the value 1000, n times, and we run 2 copies of the loop. So surely for any input n, we're going to get a value of counter being 2n. But if you have a larger value, if you run it with, say, 100,000, you actually get values much lower than 200,000. So Kira, you are right for larger numbers. And in particular, like it's not even the same wrong number each time. Like if you run it multiple times, it changes. The reason for this is basically that the inner part of the loop body is not atomic. An atomic is a word that means indivisible, like the original meaning of the sort of Greek atomos. And even though the way you implement this loop in Rust is using like atomic operations, the whole loop, like body as a chunk, is not atomic because it can be divided. In particular, between loading the value and then storing the value +1, weird stuff can happen. Like the other copy of worker can go in and fiddle with it. And this means that the 2 copies end up trampling over each other and not totally cooperating. And so this makes us sort of ask the question, okay, if we really wanted to do this properly, how would we do it? Does the operating system help us here? Does the hardware help us here? Are there things that could make this work properly? And we're not going to answer this question in this part of the book, but it will be answered in later chapters. The last of our 3 pillars is persistence. So the operating system sort of needs to be like a pillar of stability for the rest of the system. Everything relies on the operating system. And the operating system in particular is in charge of storing data. If you want to like write something to a file, it needs to go into that file and it needs to not be lost if you then turn off your computer. And if you like crash, you don't want to take the whole system down with you and like lose all your work. And so the operating system needs to be sort of robust and it needs to be able to persist data. The crux of the problem is answering the question, what mechanisms and policies are required to do this problem of storing data with correctness and in such a way that it performs well. And these words, mechanisms and policies, you should watch out for because we're going to very, very soon we're going to explain what we mean by that. And as our last example in the introductory segment, we're going to show you a program that does some I/O, that tries to persist data. And we have 2 versions of this program. We have the sort of idiomatic Rust version, the version you would really write, which is you create a file in the temporary directory, and then you write hello world into the file. But you can also write this directly interacting with the sort of API of the operating system. There's this crate called libc that you can use in Rust that basically has all of the functions that are part of the operating system's API. And in this latter example, these 2 examples are like, in terms of what they actually do, pretty much exactly equivalent. But in this latter example, you can really see the sequence of function calls: open, write, close. And to actually write data into a file, what these are calls into the operating system. The first we use to create this temporary file and open it. The second we use to write data into that file. And the last we use to close the file. So in Rust, this is implicit because when you drop the file, it closes, but we write it out manually ourselves. And these functions are called system calls. A system call is like it's basically a special name for the sort of function that's part of the operating system's API, rather than being just some library's API that you're using. And when you call them, these instructions are routed to a part of the operating system called the file system, which, as it sounds, controls the sort of files on your drive. So, in general, this is what the operating system does. It controls your physical resources, virtualizes them so they're easy to use. It handles the problems of concurrency in such a way that you can write programs that function correctly. It stores data persistently when you ask it to. Now, once you have these sort of pieces of knowledge, you can ask, what makes a good operating system? Things that it's sort of good for your operating system to do is that it can do things like abstracting the hardware. So as I said before, you might have some really weird way you need to interact with like your hard disk. The operating system will provide a function that means you don't really need to think about the particular brand of hard disk's decisions that they made when designing it. You can just say, operating system, store me some data in this hard disk, and it will go, yes, sir, I'm doing that, and I'm going to do it correctly and in such a way that you don't lose your data. It needs to perform well. It needs to protect you from misbehaving programs. It shouldn't be the case that like a single program can take down your whole computer and shut it down. It needs to be reliable. Because everything relies on the operating system must just keep trucking. Like if something goes wrong in the operating system, you're not allowed to just crash and end. You need to sort of be able to cope, provided this error is like in some way recoverable. And there are a whole bunch of other desiderata you could have for an operating system. If it's a phone operating system, you might need to be really energy efficient, or any number of things. The book also has some kind of history on operating systems. So in the very beginning, operating systems weren't really this sort of like all-totalizing manager of your programs on your computer. It looked much more just like a set of library functions for dealing with hardware. Like you might have an operating system that really just looks like a couple functions, each of which knows how to talk to a particular disk drive. So you're still kind of writing the program that controls heaven and earth yourself, but you don't have to write, the function that interacts with the drive. Similarly, like in the olden days of like mainframes that cost a bunch of money to run, a human operator would be sort of taking the role of the operating system, hence operating system. And because it was so expensive to ever leave this big mainframe idling, the operator would sort of take a bunch of people's programs that they wanted run and batch them. They would schedule these programs to run in batches. And then all of them would get done, and then everyone would get mailed back their results. And so this is sort of like the human operating system in a bygone era. Something very, very important to the operating system is this concept of the system call, being a very special library function call. It was pioneered by a computing system called Atlas. And in comparison to a procedure call, like a normal function call in your programming language, which broadly leaves the machine basically as it found it, just transferring control to some other part of your program. A system call, which is also often called a syscall, uses a special hardware instruction called trap. And as part of jumping into the operating system, that is like moving your sequence of executing instructions into operating system code, it also does something called raising the privilege level. And in particular, when you make a syscall, the privilege call changes from user mode, the privilege level changes from user mode to kernel mode. And in kernel mode, you basically have like superpowers. Like a user mode program can't go and scribble all over some other program's memory. But the kernel can, because it's the kernel. It controls all the hardware. If the kernel wants to go and edit the memory running in Microsoft Word, it's free to. Then once you've finished doing your kind of syscall, the operating system sort of undoes this operation. It executes return from trap, which jumps back into your code and also transitions back into user mode. Later in the history of operating systems, you started having machines that were really running multiple different programs at once, called multi-programming. And once you have multiple programs running at once, and these programs are being written by different people, you start needing to be able to protect those programs from each other. And so you get memory protection, and you start having to worry about concurrency. And in this sort of era, Unix, which I hope you have all heard of, was born at a phone company called Bell Labs, at which lots of other very important pieces of software were also born. And then in the more modern era, when people started wanting to have personal computers, there were actually sort of a lot of regression in terms of the competence of operating systems. Early personal computers didn't have like really important features that the mini computers operating systems did have. So for example, DOS, the sort of early version of Windows, didn't really have memory protection. So processes could screw up each other's memory. The early versions of Mac OS used something called cooperative scheduling, which meant that like one program could demand all of the CPU time. And so if you had one misbehaving program, it would just like lock up your whole computer. It would all freeze instead of properly virtualizing the CPU. But in more modern versions of these systems, Mac OS is now sort of Unix based, and a version of Windows called Windows NT sort of introduced all these good operating system innovations that make them so lovely to use. And so yeah, this is your sort of introduction to operating systems. And now we're going to move on to talk about processes. Yes, sorry, I skipped a slide by accident. So a process. Why do we care about this? In particular, we care about this basically for the same reason as we care about CPU virtualization. And we're trying to answer the question, how can the operating system provide the illusion of an endless supply of CPUs, each to be assigned to its own program that wants it? In order to do this, the operating system does something called time sharing, which is exactly what it sounds like. You run one process for a little bit, stop it, run another process for a little bit, and then keep going. And now we're going to properly introduce our two terms, mechanisms and policies. And these are basically going to be a through line from the whole book. A mechanism answers a how question. So there's a thing the operating system has to do called a context switch. How does the operating system perform a context switch? The answer to that question is a mechanism. We asked before, how does the operating system decide which processes should be run at a particular time? Answers to which questions are policies. So an operating system policy answers the question, which process should the OS run right now? No, what is a process? A process is just a program that's running. A program that's running, well, a program is a sequence of instructions, but a running program has something called machine state associated with it. And this includes a couple different things. Any given running program has memory that it owns. So if it has variables allocated in places, that's its memory, or we also call it its address space. A running program also has registers. So the stuff stored in racks and recs, if you've ever looked at assembly, these are the content of its registers. And there are some really very important registers like the program counter, the stack pointer, and the frame pointer. Also, the program may be fiddling about with files, and so it might have them open. Information about which files the program has open is also part of the machine state that the operating system has to track. At this point, we're also going to give you a first kind of quick look at the API to interact with processes. And these operations include creating processes. So naturally, an operating system must be able to make them. The operating system has to also be able to destroy processes, although often a process only runs for some period of time. Like if it's a process that sorts some lines of text in a file, that will just sort of finish. And so the OS doesn't have to destroy it. It exits itself. You also have wait, which is basically saying, don't do anything until this process has finished, which is often very useful. You can often have other ways of controlling processes too. So most modern operating systems have the ability to suspend or resume processes. If you've ever used like Control Z in a Unix shell, you will be familiar with this. And also, you can get the operating system to tell you information about the currently running process. So like how much memory is this process using? How long has it been running for? So this is the sort of thing you can do with a process using the APIs provided by the operating system. One of the most important things you can do with a process is creating it. How does the operating system do this? Well, the program, before it sort of begins running, is just like code and data on the disk. In order to start running, that has to be moved into system memory. And so this is the diagram that I've taken from the book. I'm not sure it's the clearest thing in the world, but basically you have a program stored on the disk. and then the operating system reads it and then writes it into memory. You'll note there are also some extra things put in memory, the heap and the stack. In order to allow the program to run, after putting the program's instructions into memory, the operating system allocates memory for its stack. The stack is sort of where function data goes when the program is running. And it's usually initialized with the main function's arguments. So for example, in C, you have access to arguments of the main function, argc and argv. The operating system writes these onto the stack as it's creating a process. The operating system also might allocate memory for the process's heap. If you've used Rust's collections like vec and box, these use the heap. They put things on the heap. In C, you get to sort of access heap memory using the malloc function, which will give you a pointer to some region on the heap that you now own. After it's allocated memory, the operating system also has to create these things called file descriptors, which I won't go into much detail here, but basically these are handles to the process's standard input, standard error, and standard output, which are basically streams of bytes over which input and output the program flow. After it's done all of this, the OS transfers control of the CPU to the new process's main function using this return from trap instruction I mentioned earlier, where you move from kernel space back into user space. Process can be in multiple states when it's running, and to simplify, there are kind of roughly three important ones you should think in terms of. If a program's running, then it's actively executing on a processor. If it's ready, then it's not actively executing, but it could be. And if it's blocked, then there is something it's waiting for before it will be ready. And so you can see that programs can move between running and ready basically whenever they like. And a common thing that would take a running program and make it blocked is if it asks to do some I/O. So if it wants to read something off the disk, and then that's going to take some time, that's managed by the operating system. So the operating system says, okay, you want something off the disk, I'm making you blocked. I'll turn you back into ready when I've finished getting you the thing off the disk. So here's an example of how that might flow. This table's also taken from the book. Process 0 might be currently running on the processor. Process 1 is ready to run, but currently there is no processor we could run it on, so it's just going to sit there being ready. Then at time point 3, process 0 turns to the operating system and says, I want to do some I/O. The operating system says, okay, you're blocked. And because you're blocked, you're no longer on the CPU, so I'm going to move process 1 onto the CPU. So process 1 starts being running. Then process 1 runs for a while. At time point 7, I/O for process 0 completes, and so it moves from being blocked to being ready. Now here, at 10.7, the OS could immediately start running process 0 again, but instead it chooses to keep running process 1. Then at 10.8, process 1 finishes whatever it was doing, and the operating system says, okay, great, now we'll start running process 0 again. And notably, in this sort of stream of execution, there are things the operating system has to do, like it has to stop running process 0 when it's blocked, but there are also choices it could make. In particular, the choice of whether or not to run process 0 or process 1 when they're both running already is something done by the scheduler, and it's done according to a policy. Now, because the OS is a program, and it's a fairly complex program at that, it has sort of manages its state using data structures. The operating system will store things like a list of all ready processes, a list of all running processes. It will also maintain these types of I/O operations I'm currently running. When they finish, they will wake up these processes. So it might have a map from I/O operations to processes. In the XV6 operating system kernel, which is a relatively simple one, there are a couple data structures that are used for tracking process data. So when you start and stop a process, you need to save its machine state. Part of the machine state is the registers. And so you have this sort of interesting thing where you have a structure that explicitly represents the registers of the CPU, like EIP, ESP, EBX, these sorts of things. And so when a program moves from running to ready, the operating system has to take its registers and store them somewhere so that they can be read back when the program starts running again. So it stores them in a struct that looks like this. The XV6 kernel has a couple states process can be in, more than just our running, ready, blocked. It also has states like embryo and zombie, which are kind of fun. And the whole of the sort of state that x86 maintains for a process is actually like remarkably complex. It has a whole bunch of pointers out to different things, like pointers to processes in memory, process ID for the process. It also has like pointers to a parent process. So like if another process started this process, the child process will have a pointer back to the parent process and things like this. This isn't something you need to read in detail. It's just like giving you an impression that the operating system manages a whole bunch of state about these processes. And I said before that x86's processor state has more beyond the simple three. When it's just been created, it sits in this embryo state, and if it's exited but hasn't yet been cleaned up, it's a zombie. And in particular, this final zombie state is quite useful because you may have noticed when you run programs on the shell, they sometimes return like an exit code. So a successful program will return 0, but an unsuccessful program might return 1 or negative 127 or something like that. And if you have been waiting on this process using part of the process API, you can inspect this return code before the process goes away. And so zombies are sort of useful for reading return codes out of. So kind of summary of the things I've told you. The process is a running program. It's an abstraction of a running program. It's basically program text plus machine state. The process API is the things the operating system lets you do to processes: create them, destroy them, wait on them, control them, look at their status. There are different states of processes, largely just running, ready, and blocked, but also different operating systems can have additional special states that do useful things for you. And then there is a process list. The operating system will track each process and gather them all up into a process list so it can track their state and wake them up when they need to be. The book has this process run.py script that lets you sort of have a look at how this works. Highly recommend going and doing that. It's pretty cool. And then we move on to the process API. So this is a chapter basically going in more detail about the things you can do with processes. The crux of the problem here is processes are these fairly complex things. You saw this big blob of like architectural state involved in a process. What should the OS provide to its users for them to interact with processes? What makes this sort of nice and simple and difficult to write bugs with? Particularly, we need to have all of the functionality available. We need to make it easy to use, and we need to make it fast. So a lot of thinking needs to go into the particular interface that the operating system provides. So we're going to talk about a couple different parts of this interface, and we're going to start with a function called fork. And you can see that this function libc : fork, because it's in the libc crate, it's part of the operating system's API, and so it's a system call. So let's have a look at what this program is doing. First off, it says, hello, I am process PID this. So it tells us which ID the process has. Then it calls fork, and it matches on the output. So we can tell fork returns an integer. If it's -1, apparently that must mean something's failed, so we panic. If it's 0, we say, okay, we're a child. If it's anything else, then we get a ID of a child called RC. And if this program isn't making much sense to you at the moment, that's perfectly fine, because fork is a deeply, deeply weird function. It's unlike probably most functions you've ever encountered before in that it returns twice. Because when we run this program, we see this. First, it says, hello, I am process 104450. Then it says, parent of 104451 is 104450. And then it says, hello, I'm a child, 104451. So if we go back to the previous slide, all 3 of these println statements are getting run. How's that happening? A match normally only executes 1 arm. This is pretty weird. And the answer is that here, what fork does is pretty much what its name implies. It creates like a whole copy of your program. And so hello is printed. Then we call fork. Fork sort of duplicates all of your machine state. So your registers, your address space, your open files, this sort of stuff. And then it returns twice. And the first time it returns the value 0. And this value 0 is the new copy. It tells you you are now the child. If it returns anything else, that is the process ID of the child. And so this comes to the parent. So if you got a non-zero value, you know, oh, I'm still the same process. I'm not the copy. And my copy, my child, has this process ID. So now you can see how we are getting these 3 print statements coming out. The process prints hello, announcing its process identifier. It calls fork. The OS conjures up a second process, which is almost an exact copy. It is only different in one regard, which is the return value of fork itself. And this is a point where I think it makes sense to stop for a bit, because this is just a very, very interesting thing to be able to do. But this is the core of how processes make more processes. Oh. Well, once we can fork processes, maybe we want to do more things. Notably, when you run this again, you can get the output in a different order. You can get these child and parent printlns coming out differently. So here you get parent-child, and then you get child-parent, which kind of makes sense, right? You suddenly have 2 processes. The operating system has to schedule them in some order. It could choose either way, depending on its policy. But what this means is that our program is non-deterministic. And it's non-deterministic because of concurrency. And so this is not fantastic. We'd like a way to manage this. And our second part of the process API allows us to manage this. It's called wait. So this is a modified version of P1 called P2. And what it does is that it's exactly the same, except in the branch where fork returns non-zero. That is to say, the branch where we are still the parent and we weren't copied. Or we aren't the copy, rather. We were copied. We call libc : wait. And what wait does is it just stops until your child has finished. And so this makes it basically behave exactly the same as the program before, but now we know that the output is always going to happen in this order. We're going to say hello, then we're going to print from the child, then we're going to print from the parent. So this makes everything much more well behaved. So wait is a useful function here. The last function we're going to be interested in the process API is exec. And what exec does is it changes who you are. It transmutes you into a different program. So again, very weird way of doing things. But this is, again, a modified version of our original program. We say hello. We then call fork. And this time, if we are the child, we set up some arguments in an array. Now, this is a bit noisy, but you can just sort of focus on the strings. The first string, WC, is the name of the Unix word count program. So it's a program that counts the words in another file. Then our second value in the array is p3.rs, the name of this file. And our last argument is the null pointer, which basically signifies nothing after this. So this is basically 2 arguments. And then we call libc exec with some extra things, but this is exec. And, well, what does this do? The answer is it runs the WC program. But the way it runs the WC program is by turning this program into it. So this println, where I've written this shouldn't print out, literally never runs, because the moment you call exec, you're gone. You're gone from this program. You're another program now. And so when we run this program, what will happen is we will fork. The child will turn into WC. The parent will wait for that. And then it'll say, hello, I'm the parent. So this is what we get as output. We say hello. And then we say p3.rs has 18 lines, 62 words, 586 characters. And then we say, hello, I'm the parent. And this is just again, pretty crazy, pretty cool. this is a way that we can use the operating system's API to run other programs, because we can fork ourselves and then turn our child into the program we wanted. Give that a moment to sink in. Again, super weird. I'll show you the code again just so you can have a quick scan over it. Fork, then the child execs while the parent waits, and then everything cleans up in order. So why do this? Why do it this way? In some ways, some clever people have said this is not a great design, but there are things to be said in favor of it. In particular, the fact you separate fork from exec. You first copy yourself, then you turn into another program, instead of just saying, like, create this other program. Actually is very, very special because it allows you to write your own command line shell. It lets a program you write fork itself, run some code, and then exec the thing you asked for. So in using this API, you can write, this prompt that when you open a terminal, you could write that yourself using this API. First of all, you can print out your prompt, like the $sign or whatever, and then read a command from the user. Then, once you've got the command from the user, you can fork yourself, set up the user's command that you were given as the arguments, then exec that and wait for it to complete. And once it comes back, you can print out its output to the user and then give your next line for the user to put a new command on. So this ability to get in the middle of fork and exec and write your own stuff in there is immensely helpful, because it makes writing programs that deal with processes really, really powerful. So exactly how might we be wanting to run code between fork and exec? Now consider this command. So this command says, count the words in p3.rs and write the output to a file. This arrow sign, if you're not used to shells, says, take the output of this program and don't show it to me. Instead, just write it into this file. And the way this is done is after the shell has forked, but before it execs, it closes its own standard output, which, to be clear, is the child's standard output. And then it opens new file.txt. Because of the way Unix hands out file descriptors, closing standard output and then opening a file sort of replaces standard output with that file. And then when we turn ourselves into WC, into word count doesn't need to know any of this. It just has its own standard output replaced with the file. So it runs as normal, and its output just lands in new file.txt, which is so elegant. And so here's how you'd write a program that redirects its own standard output to a file. So this is a tiny little version of what is almost a shell. You fork yourself. Then if you're the child, you close your own standard output. Then you open the file you wanted to write into. Then you turn yourself into WC. If you're the parent, you just wait for that to finish. So when you run this program, you don't get any output, which is what we intended. And then if you go and read what's in p4.output, you get the output of word count. And so we have we've managed to trick this child program into behaving completely normally, but putting its output where we wanted it. If you've used pipes while using a shell, so piping the output of one file to another file, they work in almost exactly the same way, where before you exec, but after you've forked, you go shuffle around which file descriptors are pointing where, so the programs write their output and take their input from the right places automatically, none the wiser. The last bit of the sort of API processes that the operating system gives us is these sort of control components. So these things called signals. There's another system called kill. Kill is a bit much. It doesn't always kill things. It just delivers a signal. It just so happens that most of the signals say stop. Yeah, you can quote unquote kill a process, and that just means the process receives some signal that usually means some sort of imperative action. For example, when you type Control C in a shell to try and stop a program, that sends a signal to the process, and in particular, the signal is interrupt. If you do Control Z in the terminal, that delivers the signal stop. There's also another system called Signal, which allows the process to catch signals and respond in their own way. Modern operating systems often have their own users, which are sort of like a special process that controls some subtree of the other processes. So it makes it so that one person logged into a computer can only control a subset of the processes on the computer, which is very nice if you have like a big server that only a couple of people have permission to use. And so it prevents one user from killing the processes of another user, but leaves them perfectly fine to kill their own processes. Following on from the concept of a user, there's also the concept of the super user that is typically called root on most Unix systems. And root, because they are sort of the root of the process tree, controls every single process and could do lots of other things too. Most of these operating systems come alongside well-integrated tools for interacting with processes, like PS shows you like a list of all the running processes. Top shows you like which processes are using the most resources. There are sort of nicer, more modern versions of these programs, but the old ones work perfectly fine. There are also the command line versions of these system calls. So like there's a command called kill and a command called kill all that allow you to use your shell to sell signals to processes. To sell signals? To send signals. I apologize for the slightly weird way I'm talking. But yeah, you have tools that you can use to interact with processes. It's pretty sweet. So yeah, in summary, the process API is really powerful. There are ways in which it's weird, like forking and then execing is a bit strange and has been criticized. A fairly recent, fairly well-regarded piece basically says, this is a relic, we should stop using it. There are other OS APIs that should be used instead. But it's sort of the oldest and the most well-used one. But yeah, Rust in large part does agree with this criticism. There's no way naturally using the Rust adapted library to fork your program. Instead, Rust builds these up into like higher level abstractions. So if we wanted to do the same thing we were doing with our earlier programs using the normal Rust standard library, we'd just say, command new wc arg p3.rs and then run it, which is a much more natural feeling way of doing this, but does sort of hide under the hood the exact way that the operating system is doing it. And so the final homework of this segment is fork.py, which you can use to simulate trees of processes doing this sort of thing. And yeah, there's a bit of programming homework that will allow you to play with these tools. I highly recommend doing this. And yeah, so this is Operating Systems 3 Easy Steps, chapters 1 to 5, in high-level summary. I highly recommend actually reading the chapters yourself. They're much richer than what I've presented to you. This is a very high-level summary. And also there are some dialogues in chapters 1 and 3 that are quite entertaining. I'd highly recommend you read those. So yeah, but I hope for those of you who have not yet read the book, I have given you a nice taste that has made you excited to read the book, and that you might continue sort of engaging in our book club. I think with that, I will sort of yield to discussion and any final questions. Oh dear, I hope I'm not. Oh yes, good, great. Sorry, hadn't yet tabbed out from my presentation, so I didn't actually know what was happening. I was suddenly struck by the fear that it had gone wrong like 40 minutes ago, and I had no idea.
No, you're
Anyway,
right.
fantastic.
That was great. I like the quote they had about it being most important that it's right.
Yes.
But what it said the principle was Lamson something principle.
Yeah. I'll hop back 1 second. Was it this? Yeah, Lamson's law. Get it right. Neither abstraction nor simplicity is a substitute for getting it right. Yeah. And to be honest, like I think there is some sense in which this API for processes is really elegant and really beautiful. But it's like I think it's very elegant and very beautiful as like a set of operations that like form the building blocks. And that the majority of the time, the thing you actually want to do is just fork and exec all in one without doing any funny business in the middle. And that ends up looking a lot more like Rust's std process command, um, which also prevents you from invoking undefined behavior by doing this, which is also quite nice. But yeah. So yeah, I suppose you can tell. I'm sure you can tell that I've found the first couple of chapters of this book really cool. Um, oh yeah, says you're lazy. What happens if you use weight and the child? Terrible answer. I don't know. My assumption is that it would probably just return immediately because there's nothing to wait for, but I could be wrong about that.
Did anyone on the call have a go at the homework? And if so, what did you make of it? I say as someone who did not try the homework or finish reading the chapters.
Yeah, I mean, they'd be in good company, for I also have not properly attempted the homework. I have only read the chapters.
I think it will be humbling having not done any homework for a while.
Oh, that's nice. Yeah, yeah, that is nice. So yeah, apparently Perl has system which does fork exec and wait all in one go, but they also separately have fork exec and wait, which sounds quite neat. I do feel like probably fork like could be made memory safe. Like it doesn't seem immediately like it's a dangerous operation. It's a super weird operation, but like I feel like there's a fork like thing that could be made memory safe and could be made part of the standard library. But that I would need to think about it. Maybe there are some invariants that it would break. Like I don't know, maybe it means that you can like duplicate references to files that you would then be able to base on or something. Um, but um, but yeah, it's a sufficiently weird and wonderful interface that I now find myself wanting to use it for things. Ah,
And maybe read the outcome
yeah,
code just for the recording as well.
yeah. So apparently, if you call wait in the child, it doesn't crash, but it will return -1, and it will set Erno to each child. So like I was kind of right in terms of the behavior, but it also does have like a whole bunch of extra information it gives you, which is quite important.
Yeah, I personally I really like this fork execute section because like coming mostly from Windows programming, you only have like create process.
Mm-hmm.
But on the same time, I'm wondering a bit like, is it like how heavy is it to like fork and then exec? Is it probably it's optimized quite well by the operating systems because they get down that route?
Yes. So actually, I'm reasonably confident of this. I'm not
Yeah.
like 100% confident, but let's say I'm like 97% confident. The way fork and exec are implemented in at least Linux is by using copy on write memory. So when you fork your program, it doesn't have to like copy your entire address space into a new part of physical memory. So like imagine you had like 2 GB of string data stored on the heap, and then you called fork. You might initially think like, oh God, I know how to do a 2 GB copy. But what I think the operating system does is it basically says those pages of memory are going to be shared up until the point one of the two processes like tries to mutate them. And if one of them tries to mutate them, then we'll copy the page to a new place of physical memory, and then they'll become different.
That makes a lot of sense.
So yeah, I think it means that if you're forking and then not really editing much, it's actually like very cheap to do.
Any more questions before we wrap up? We're planning to do the next few chapters in 3 weeks, so that should hopefully give folks time to give the chapters a read. It will likely take us up to chapter 8. TBD whether or not we'll cover all of chapter 8, but we're hoping to. So if you're able to read up to that, that would be great.
Yeah. I'm not sure. Did we share like Discord already? Maybe we.
No, that's a good point. Is there anyone here who's not in the Discord who would like a link? Yes, okay. Oh, you got it already. Great, Tim. Thanks. And yeah, apologies for the gate crashes earlier. People seem to find our meetup through Rust the game, but it's definitely increasing the frequency with which it's happening. So we might need to have a think about a different approach for continuing to have like an open meetup where people can post stuff and unmute themselves and join in and do talks, but also kind of not allowing people in who aren't there in good faith. So we'll have a think about best process for doing that. Cool. Should we wrap it up then?
Yeah, thank you all for coming.
Thank you.
Yeah.
That was great.
Thank you much for the very nice preparation.
Set a high bar for anyone who's thinking of doing chapters. It doesn't have to be that polished or
Yeah, no,
that
yeah,
complete.
don't worry. I
Um,
just like using types.
but it was very, very worthwhile. So I hope Cosmo will be up for taking a few more chapters later as well.
Yes. Cool.
See you
See you
soon.
around.
Bye.
Bye.